In calculus class, we're going to look at another application of the definite integral. So this is center of mass. And in this one, we got constant density. And the reason why this is important, this is how we calculate it. Like we're trying to find a center of mass that's like the center of mass for x and the center of mass for y. It's a single point that when I balance this parabola-looking shape over it, if you can imagine like this fulcrum that's underneath here, and wherever that point is, that's the center of mass, this thing won't tilt in any direction. It'll just be perfectly balanced right there at that center of mass point. So that's what I'm looking for. That's the notation that we use for the x bar and the y bar. But what I want you to see, this is the formula that it gives you in the book. It doesn't talk about the y formula, but it's the same concept. It's the y, the density in the y direction, dy, and then over the integrals of the density in the y directions, dy as well. Again, that's the formula for mass on the bottom, the mass over the whole entire region. And then up top, these are called the moments. And that's how we find the center of mass, okay? Now, why is it so important that we say constant density? Well, remember, because we're integrating, if I have a constant, if this thing is a constant, and it's the same density function top and bottom, remember, constants can come out of the integration. And when we do that, these will just cancel away because it's the same constant in the top that it is in the bottom. All right, so constant density, and I have symmetry. You can see I'm perfectly symmetric over the y-axis. So that means for sure I'm going to have 0 as the x coordinate of the center of mass here. So 0, and then we have to find the y. Now here's how I approach these. So pick some rectangle. So we're when we have the d, the dx, the dy, we are like infinitesimally thin. So these rectangles would be like so thin that they look like just lines. But just for the visual purposes of it, consider it as if it were a rectangle with a thickness delta x. Okay, that's how thick that is. Let me put that over top of it so you can see it. Now this is a rectangle, and in that rectangle somewhere is a point that would be the center of that rectangle. And since it's uniform density, literally it would be the exact center of that rectangle. It would be some x coordinate that our textbook uses this little squiggly line, and a y coordinate squiggly line. And that's the center of some rectangle. That is one of the many rectangles that we could create, for a certain size delta x. We could create all these little strips, and all of them would have, a midpoint in there somewhere. So just imagine that's what we're doing here. We've got all of these different midpoints, right? And because of the symmetry and the uniform density, the fact that some of these x's are positive, some of them are negative, they're going to cancel out. That's going to give us the 0, okay? But for the y's, you're going to get this pattern of the y midpoints being like this. And what it's going to come down to, because of the constant density, it's just the area is going to be the weight that we put on these y's. So like, if I just did 11 plus 10 plus 9, and found the average of those three, you could see that I'm just going to get 10. But if I made 11 count one time, and 10 counted twice, and 9 counted 3 times, and that's 1, 2, 3, 4, 5, 6 total things that I'm averaging here, I get a total 9.6 repeating. And you can see that the weights that I put on this number brought the average down closer to that number rather than the other two numbers. It's pulling it down because those numbers are weighing more. So it's like a weighted average, but because it's an integral, definite integral, it's an infinitely long weighted average. All right, now let's come up with what are we averaging here, okay? So again, all we need are the y's. So I'm not worried about the x's. The y's, how do I get a y? How do I get an average value of a y? Well, it's just the upper number plus the lower number divided by 2 will be the number in the middle. So it's the upper number, which is 12, plus the lower number, that's the 3x squared, and I'm dividing that by 2. That'll give me that number that's dead center. Okay, and again, if it's uniform density, constant density like this, then it is going to be that number in the middle. All right, now the area, like I said, the area of each one of these rectangles is what's going to be the things that we use to weight it. So the area is length times width, right? So the length is how long is this? Like we talked about in the previous videos, we can get that via subtraction. It's the 12 up top minus that function on the bottom, the 3x squared. All right, and then what's the width? The width is delta x. All right, so the weighted average here, again, would be the y's, the midpoints, those values in the middle there, every one of those, times the area where that y is the midpoint. That's what's weighing it and making them count more or less. And then what are we dividing by? We're dividing by the weights. We're dividing by this 12 minus 3x squared dx, which is like the total amount of the area. That's like the total area of that whole entire region. And then up top, it's the areas times the value in the middle. Now, when we take a limit as delta x goes to 0, this becomes an integral, right? And then this becomes our functions. These just become the 12 plus 3x squared over 2, the 12 minus 3x squared, and then the delta x becomes dx. So there's what we have to set up and solve to be able to do this. And then use Desmos or some graphing technology to help you find a and b. A and b here are the 2 and the negative 2. All right, so again, we know that x is going to be 0. The center of mass for y is what we're finding here. All right, I've got a 1/2. I'm going to pull that 1/2 all the way out of this integration. Up top, this is 12 plus 3x squared times 12 minus 3x squared. If you recognize that, that's a difference of squares factored form. So I can square the 12 minus, I can square the 3x squared. That'll be 9x to the 4th. And that's what I'll get when I multiply that numerator together, dx. All right, on the bottom, this is ready to start being integrated. So that's going to be a 12x. This is going to be a 3x cubed over 3, or just x cubed. And I'm plugging in 2, I'm plugging in negative 2. All right, likewise up top, I'm going to have a 144x minus, this is going to be 9x to the 5th over 5, or 9/5 x to the 5th. And all of that over 2 goes in. That's going to be 12 times 2 minus 2 cubed is 8. All right, and then minus negative 2, 12 times negative 2, I should say. Minus a minus would be plus, then negative 2. All right, just doing the fundamental theorem of calculus there on the bottom. And sorry, I left off my 2 and negative 2 there. So I got a 144 times 2 minus 9/5. It's 2 to the 5th. All right, again, minus plugging in the bottom number. 144 times negative 2. Minus a minus would be a plus 9/5 negative 2 to the 5th. All right, there's the top. All right, all that on the bottom works out to be 32. All right, all that stuff in the numerator works out to be 1152 over 5. And the 32 on the bottom, that works out to be 36/5 once you simplify this. So what does that even mean? What have we done here? So if you go down to the next line here, and remember we said our x-coordinate is going to be 0 because of the symmetry of the y-axis, and then you do 36/5 for the y-coordinate. So what this says is that is our center of mass. That is where I would have to balance this thing, that picture that I drew before. If I put the point right there at 0, 36/5, that was where my fulcrum rested. Right, this thing would balance perfectly. It wouldn't, maybe it would tilt eventually when I let go of that parabola shape, but eventually it would find its balance if I made the center point exactly there.